So we're going to work on springs. Some things to keep in mind. The idea behind springs is this, is they come in two varieties. You can have a compression spring, which could actually also be one that you can stretch as well. So this one, however, not really compressing it too much. This is all stretching. Okay. The idea is this, though. They have an equilibrium position. They have a nice relaxed, for example, from this hand to this hand. Right there is its nice, unstretched, uncompressed, relaxed position. But the farther we move it off of that position, the more I push it in, for example, or in the case of this one, if its relaxed position is here, the more I move it from that position, the harder it pulls against that motion. So if I move it to my right or your left, it pulls back this way. And, this is important, the farther it's moved, the more it pulls or pushes, the bigger that force is going to be. So the force is dependent on the distance you've stretched it. Taking this rubber band, which follows basically the same principle, and stretching it a couple inches, I have to, apply a force to keep it stretched. Not too bad. If I stretch it out to here, this is actually pretty difficult. I'm not going to be able to do this for 10 minutes and not be tired afterwards. So this is a much harder, much larger force. So that's one idea, is that the farther it's changed off its equilibrium, the bigger the force is going to be. So the force is dependent on the distance it's stretched or compressed. But not all springs are created equal. Stretching this one, well, that's not too bad. I stretch that, 30, 40 centimeters, right? I'm not going to be able to stretch it. This one applies a much larger force for this as you pull it apart. So this is a much stiffer spring. It's a much looser one. This one somewhere in between. I think you would agree. Like this one I can compress with one hand, or with my bare hands. This one, I'm not even. How long are we going to wait before I got to work out for a while before I would be able to compress this noticeably. So we need a number that describes the difference between springs. They follow the same law, but there's something about this one that's much stiffer, and it applies a lot more force for a given distance. And so the idea is this. Hooke's law says that the force that a spring pulls with is really dependent on the distance. I'm going to write that over here. So it depends on how far it's stretched from equilibrium. The key is there, it's got to be from its equilibrium position. And I'll show you that over here in a second. But what also matters is the type of spring. This spring has the ability to produce a lot more force if you move it the same distance as this one. So that value is called K, and it's known as the spring constant. And it depends on the type of spring. Different springs are really described by that spring constant. It's not their length that matters, really. It's not their diameter that matters. What really matters is how much pullback do they give you. So, for example, this spring, when I hang it up here, and then hang a force, apply so its equilibrium position is right now, it's in this neighborhood at the end of the spring. If I apply a force of 10 newtons to it, here, let me make the screen bigger so you can see it. So let's go back. Unstretched. Equilibrium position's right here. Unstretched. And then when I stretch it, we're talking about here. So the x that you see in that equation that was on the board is this. It's the distance from unstretched to stretched, from equilibrium to not equilibrium. And right now we have 10 newtons worth of force on that, right? 1 kilogram mass times 9.8, so we'll call it about 10 newtons. Now notice this spring, that's its stretch. But if I look at a different spring, I don't think it'll even be worthwhile to do this one. I won't be able to notice it. But if we do a different spring, say this one, notice its unstretched is over here. That's fine. It may start higher. Let's see if it stretches farther or less far. And if I let it hang down, it actually goes to about here. So notice its x value, this is less. So this spring, for the same force, doesn't need to be stretched as far to produce that force. So this spring right here would have a larger value for K than this one would. This would have a smaller value of K. Right. The smaller the value of K, the stretchier the spring is. This would have a large K, and this would have a much smaller K. So, in a minute, we're going to actually find the K value for a couple of these springs and see how that works. But for now, this is basically Hooke's law, and we're going to add one more thing to it. When you look at it in your formula sheet, there will be a negative sitting right here. And all that negative means is what I mentioned earlier, and that is that the spring will always pull against the way it's been pulled. So if the X that we had up here a minute ago, if that distance it stretched is, here, we'll do it over here. The distance for this one that it was stretched was down. Well, which way is the force by the spring? Up. Here, if I stretch it to my right, the force is back to my left that it pulls on my hand with. So the force by the spring will always oppose or be in the opposite direction from the direction that you pulled it. That's all this negative means. For the most part, we don't have to worry about it too much when we're doing a problem. So let's see if we can find the K value for these two over here. If you look at the chalkboard over here, so we have the following. A couple different examples. Let's figure out both these K values. So over here, for the spring that's currently up there, force by a spring is equal to the K value. I'll call this, we did this one second, so I'll call it 2. So K2 times X2. Now, what's the distance that it moved? Well, I got this. I have over here, handy dandy ruler. So the distance that this one stretched approximately is about 9.5 centimeters. So I know this value is 0.095 meters. Also, this is 1 kilogram sitting here, so I know that this is 1 kilogram times 9.8, so it's 9.8 newtons worth of force. Notice, that's how hard the spring is pulling. Why? Because this thing's in equilibrium. It's not accelerating. The downward weight of this must be equal to the upward pull by the spring. So I can use my knowledge of equilibrium to know that the spring has to pull with 9.8. So that means I have 9.8 newtons equals K times 0.0, this is not the K value, this is the X, my apologies, 95 meters worth of stretch. And I can divide real quick and get the, pardon me, I had to pause the video because I have a calculator. Who does that? So I've got 9.8 newtons divided by that 0.095, and I get a K value for this spring of about, well, I'm going to round about a 103. Now what is that? 103 what? 103 chickens? What's my units here? Well, when we divided, we had newtons, and we divided by meters. So the units of this are how many newtons you get per meter of stretch. Now, just because it says per meter of stretch, please don't think that in order for this to work, you have to stretch something a full meter. Most of the springs we have, we're not going to be able to do that with. Don't think like that. I mean, if you buy, American cheese at the grocery store and it's $6 a pound, does that mean you have to buy a pound? No. That's just the rate at which it's sold. It's the price rate. It's the dollars per pound. We need something to compare it to. So in this case, it's newtons worth of force per meter. So this would have a K value, this particular spring, of 103, about 100 newtons per meter. Now, what about the one we had up there earlier? It is going to have a K value of, so we put the same force on it, and make sure that we read this correctly, but same force, it's down to here, so its value of K, we can work this one out if you'd like. In fact, let's do this. How well can we see that board? We can see it pretty good. So we know the force by the spring is K, distance stretched. So we can call this force 1, K1, X1 for the first spring that was up there. And that K value is going to be the force divided by the stretch. We did that over here as well. So in this case, our K value is going to be 9.8 newtons, same force, divided by this stretch, which is in the neighborhood, of course, I'm using chalk, about 25 centimeters. So 0.25 meters, of course. So I had 9.8 divided by 0.25, and I get about 39. So the K value here is 39 newtons per meter. So you can see this spring stretches more for the same amount of weight. Now, how far do you think this spring will go if I hang another kilogram on it? Well, I'm thinking if I double this force, right? If I double this force and the K is the same, right? It's always the same. Important to note, this K right here, or this one, for example, that's a property of the spring itself. So once you know that, this spring will always have, unless it gets damaged in some way, it will always have that value for K. This is not unique to the situation. This spring will always have that number. Now that I found it, I know it. So if I hang twice the weight off of it, it should give me twice the stretch. I should be able to go, let's see, if it was about 25 centimeters before, and sure enough, look at that, it's about 25 again. So this double the force, double the stretch. Seems to make sense. Another property or another aspect of springs that we want to look at is this. We want to look at the energy stored in a spring. If you looked at kinetic energy, the mathematical form of this equation is going to be familiar to you. The energy stored in a spring, we use U, capital U, for potential energy quite a bit. You can find that, well, let's see. It depends on what. Think of a rubber band. All right? If your face was this chalkboard, and I did this, it's no big deal. All right? Here, let me make it bigger so you can see what I'm talking about. I got to remember to do that. So, this is your face. If I do this, it's annoying. But if I do this, it's downright threatening, right? Which case do you think has more energy? If I stretch it a little bit, not a lot of energy. But energy is all about, noticing energy is all about what can hurt you. That's at least works for me. And this, if your face was right there, you would not feel comfortable right now. So, the farther you stretch it, the more energy is stored in the spring. Seems to make sense. So, exactly how much energy is stored in that spring? Turns out, depends on the mass. Not the mass. I'm thinking about kinetic energy. That's funny. It doesn't depend on the mass. Mass of the spring is not important here. The K value for the spring and how far you stretch it, but how far you stretch it really matters because it's squared. And of course, there's a half out in front. Interestingly enough. So, just like kinetic energy, if you've looked at that, is 1/2 m, you see why I got m earlier, v squared, where velocity is the item that's squared there. In this case, it's the distance you stretch it. But the mathematical form, by the way, is the same. So, one of the things I want you to keep in mind with this is the squared part. Multiple choice question, they're going to do things like say, all right, if I stretch it this far, I get a certain amount of energy. What if I stretch it 3 times farther? Instead of there, what if I stretch it to here, for example? So, if this is my original stretch, and this is 3 times that, be careful. If they ask you how much energy, it may be 3 times the force, but it's actually 9 times the amount of energy. Because that 3x, that factor of 3, is going to get squared. And you're going to end up with a factor of 9x squared. You're going to end up with 9 times the original energy. So you want to be careful. If they multiply, or not multiply, but if the distance it's stretched goes up by a factor of 5, it's 5 times longer, then you have 5 squared. You have 25 times the energy. So be careful about that with the square. For now, I think that's fairly good. I think we'll do this in another video because it's long enough. But these are the basics of springs right here.